Hello, and I would like to start this lecture by illustrating how useful this scaling property is. So moment generating function of random variable x multiplied by constant a is easily expressed in terms of moment generating function of the original random variable x, the property which I proved at the very end of my previous lecture. So also I would like to remind that for random variable x being gamma distributed with parameters alpha and lambda, the MGF capital M sub x of t is 1 divided by 1 minus t over lambda raised to the power alpha for t less than lambda, and it's equal to infinity otherwise. So, and now I want to find MGF of random variable c times x, where constant c is greater than 0. So it's my constant a here, but here a can be positive or negative, but gamma distribution is positive. Gamma random variable is positive. I multiply it by a positive constant, and the claim is that it's still going to be gamma distributed, but with different values of parameters. So m of cx at point c is mx of ct. And therefore, now ct should be less than lambda, or t should be less than lambda over c. And it's going to be 1 minus ct, but I can take c from numerator here to denominator of denominator, so it will be 1 minus t divided by lambda over c to the power negative alpha. So let me square this formula. And t is less than lambda over c. So when I look at this guy, I recognize that this is moment generating function of a gamma random variable with the same shape alpha, but the scale is now lambda over c. Hence, by the uniqueness theorem, c times gamma variable with parameters alpha and c is also gamma variable with the same shape parameter alpha, and oh, I'm sorry, it's not c, it's lambda here. Yeah, and my new intensity or scale, but its parameter lambda, is now lambda over c. And this is true for any positive c. Now, in the case where I choose c equal to lambda, so if I set c equal to lambda, lambda over c becomes 1. So I conclude that lambda times gamma of alpha lambda, it has the same distribution as gamma random variable with shape parameter alpha and intensity equal to 1, because lambda over c becomes 1. So let me also square this result. Okay? And at this stage, I would like to remind you that at the end of our discussion of chapter 2, I mentioned a particular result about two gamma random variables, x1 and x2. They're both gamma with different shape parameters, alpha 1 and alpha 2, but the same intensity beta. So beta here and there, they are the same. And I proved, but I only proved in the special case of beta or lambda equal to 1, that such a ratio of x1 over x1 plus x2 has a particular beta distribution. And I explained then that I will do the rest. I will reduce general case to the special case addressed then later on during the consideration of moment-generating functions. Let me remind what specifically I'm referring to. This is slide 14 of part 5 of chapter 2 notes. And this was discussed in lecture 12. And so in the also see the record of lecture 12 at around 1 hour 23 minutes. Yes, so it was in the second half of lecture 12. That's when I discuss this result. And there was a slip in the chalk at that lecture. And that's actually how the formula should look like. I multiply gamma variable by lambda, which is the same constant as the intensity. So the result of such scale is gamma variable with the same shape alpha and new intensity parameter lambda being equal to 1. And so for beta, which is the same as lambda, equal to 1, this was already proved in lecture 12. Now, for a general beta greater than 0, my random variable y sub 1 may be rewritten as so what I'm going to do is I will multiply both constants. I'm sorry, I will multiply both numerator and denominator by the same constant. So technically speaking, I have the first gamma variable with parameters alpha 1 and beta. It's the first gamma variable divided by the sum of the same variable, gamma 1 with parameters alpha 1, comma beta, plus the second gamma variable, gamma 2, with parameters alpha 2 and beta. And an obvious trick now is to multiply both numerator and denominator by constant beta. So I have beta here, and then I have the factor of beta here and there. Okay, so y1 can be rewritten in such a form. Then what is obvious is that when I multiply gamma variable by beta, I obtain another gamma variable with intensity equal to 1. And let me rewrite it over there. So therefore, y1 becomes gamma 1 with parameters alpha 1 and 1 over the same variable, which is gamma with parameters alpha 1 and 1, plus the second gamma variable with parameters alpha 2 and 1. Yeah, so the shapes do not change. And of course, when I multiply a random variable by a constant, nothing is going to change. Like there's still, what I'm saying is that these two variables are still going to be independent. And I have also mentioned that when I add up gamma variables with the same shape parameter, but with different, I'm sorry, I add gamma variables with the same intensity beta, or here it's 1, but with different shape parameters. So if they are independent, the sum is again gamma variable with the same intensity parameter and with the new shape parameter equal to the sum of the original shape parameters. That's actually what I proved in the special case, but this is also true in general. And for such a ratio, I already proved that it's going to be beta distributed. So please refer to my lecture number 12 and my random variable y1 is going to be, like I denoted it by v, so it's going to be beta distributed with parameters depending on the corresponding parameters alpha 1 and alpha 2. So it's going to be beta random variable with the first parameter being alpha 1 and the second parameter being alpha 2. So this result was proved in lecture 12 for the special case of beta equal to 1. But because of this nice scaling property of the gamma family, so when I have general intensity and I multiply by lambda, I reduce this to gamma variable with intensity equal to 1. But since I have two gamma variables in numerator and denominator, and the scale is just the same thing, so I can multiply numerator and denominator by the same thing, and the ratio is, of course, not going to change. So this is a very simple reduction of the special case to the general. Like special case is basically the same as the general case, just because of this nice scaling property. And what I also want to mention in relationship to this observation is that I obtain a nice additivity theorem for the gamma family. I proved it in the special case. So I proved that for intensity equal to 1, such a sum is also gamma distributed, but things become pretty simple when we employ the techniques of moment-generating functions, which you did not learn yet at lecture 12. But what we obtain is that if you have random variable x1, which is gamma with shape parameter alpha 1 and intensity lambda, then we have random variable x2, which is gamma with shape alpha 2 and intensity lambda, it's the same intensity, etc. And finally, a random variable xn is gamma distributed with shape parameter alpha n, but the same intensity lambda. And x1, x2, xn are ID random variables. I'm sorry, the independent random variables. They are not necessarily identically distributed because alpha i's can be different. Then x1 plus etc. plus xn is also gamma distributed with the new shape parameter equal to alpha 1 plus etc. plus alpha n and the same scaling parameter lambda. The proof of this result is pretty straightforward. What we need to do is just to use the moment generating functions and the multiplicity theorem. So we need to use multiplicativity theorem that moment generating function of the sum of independent variables equals the product of their moment generating functions. So what we have is the following. Yes, so we have random variable xi, which is gamma with parameters alpha I and lambda. So then the MGF of xi is given by this formula. Okay, and therefore the MGF M of the sum x1 plus x2, etc., plus xn at point T is going to be the product over I from 1 to n of 1 minus T over lambda to the power negative alpha I. And for each of these results, T is less than lambda. So therefore, everything is going to be finite for T less than lambda. But when we look at this product, so we see that it's going to be 1 minus T over lambda to the sum of negative alpha i's. So therefore, it's expressed in exactly the same form. So what we conclude is that AM of x1 plus x2 of xn at point T is simply 1 over 1 minus T over lambda raised to the power alpha 1 plus etc. plus alpha m. And T is less than lambda. So when you look at this representation for the moment generating function of the nth partial sum, so you immediately recognize it as moment generating function of a particular gamma variable with the shape parameter alpha 1 plus etc. plus alpha n and the same intensity lambda. So, and then we just apply the uniqueness of correspondence between moment generating functions and the distribution. So if we identified moment generating function of our distribution as that of a particular member of the gamma class, then it solves the problem. So we immediately identify the distribution. Okay. So for now, we finished with the gamma family. And I want to discuss the following important result on how to find moment generating function of a shifted random variable. So random variable x is what causes randomness, and we just shifted by constant a, which can be positive or negative. Okay. So, in order to prove this straightforward property, simply rewrite MGF, which is expectation of e to the power t times a plus x as the expectation of the product of e to at times e to tx. And then e to at is a constant. So for each fixed t, it's a constant. Therefore, it can be pulled outside the expectation sign. Hence, it's equal to e to at times expectation of e to tx. And since this is moment generating function of the original random variable x, so obtain that it's e to at times m sub capital X evaluated at point t, which ends the story. Okay, so it's a simple result, but it's important to stress it out since we don't want to derive it from scratch every time we need it. So our next result is given as theorem 345 part B on page 166. So this multiplicativity property is theorem 345B on theorem 166. And the way it is proved as that m sub x plus x of t is by definition expectation of e to tx times e to ty. And then for a fixed argument t, so e to tx is actually g sub t of capital X. This is h sub t of capital Y, where g sub t of u is e to tu, and h sub t of v is e to tv. So I just prefer to use two different functions, two different arguments, since I don't want to mix apples with oranges. Yeah, and then I have a characterization of independence of random variables x and y, which I already discussed before. Random variables are independent if and only if for an arbitrary pair of functions g and h, which are non-random functions. These are non-random functions. Yeah. So expectation of the product of g of x times h of y equals the corresponding product of expectations. So when I discussed covariance and what is behind it, I mentioned this important characterization of independence. It's not sufficient for expectation of x times y to be equal to the product of e of x times e of y. But if we can have flexibility with functions of x and of y, then we are okay. And that's exactly where we are now. So x and y are independent, therefore the product of functions of these two variables equals the product of their expectations. Yes, therefore MGF of the sum equals the product of the corresponding moment generating functions. So therefore, m sub x plus y of t equals expectation of gt of x times expectation of ht of y, which is expectation of e to t times capital X times expectation of e to the power t times capital Y. And these guys are the corresponding moment generating functions of random variables x and y. That's the end of the story. And as I said in the previous lecture, so this property by induction can easily be generalized to the sum of an arbitrary fixed number of independent random variables. So I would like to mention that I already evaluated the moment generating function of the standard normal variable in the previous lecture 15. So okay. So let me remind you that MGF of standard normal variable z of argument t is simply the exponent of t squared over 2. And now my random variable x is a linear transformation. So it's normal with mean mu and variance sigma squared. So, but general normal variable x is actually equal to mu plus sigma times z. Why? Because x x minus mu over sigma is distributed as the standard normal variable z. This is the procedure known as standardization. And that's what we discussed before. So we solve this equation for x to get that our general normal random variable x is mu plus sigma times z. And what we can conclude is that m sub x of t, so moment generating function of such transformed variable, is going to be this constant mu, which is constant a on slide 19. So it will be e to the power mu times t times moment generating function of variable sigma z. So it will be e to mu t times mgf of random variable sigma z evaluated at point t. And we go further backwards. So when you multiply random variable by a constant a, but it's sigma in our case, it's the same as moment generating function of original variable at point at or sigma t. Hence, m of sigma z evaluated at point t is mz of argument sigma t. And we still have this factor e to mu t, which we need to carry over here. But moment generating function of standard normal was already found in lecture 15. So we just need to use argument sigma t in lieu of t here. But we obviously obtain that for the general normal, it's going to be the exponent of mu t plus sigma squared times t squared over 2. So that's what I discussed in the previous lecture, where I showed the graphs of this function for various values of the mean parameter mu. So, and this is a nice illustration of why such simple formulas relating moment generating function of scaled and shifted random variables with the original moment generating function of original random variable x. So you see how useful these formulas are, because it gives us the formula for the general case of the normal distribution at no cost. Okay? So now let's go backwards. So we got this formula, and let's go backwards. I want to rederive the original result from this theorem, just to make you practice with switching back and forth. Okay, now we have general normal variable with moment generating function equal to the exponent of mu t plus sigma squared times t squared over 2. And we now want to find moment generating function of the standardized variable y, x minus mu over sigma. Okay. So what I want to do is to represent our standardized random variable y as 1 over sigma times our random variable x minus mu over sigma, or as negative mu over sigma plus 1 over sigma times x. And then I'm going to use the previous results that m sub y of t is going to be equal to this constant actually is our constant a, and we need to employ the property about shifted variable. So we employ this property too, that when we have random variable shifted by constant e, we get this multiplier e to the power at. So, but therefore, we get this constant a being negative mu over sigma. Therefore, it will be exponent of negative mu over sigma times t, multiplied by moment generating function of random variable 1 over sigma times x evaluated at point t. And we now need to find MGF of 1 over sigma times random variable x. So we use this property 1 on slide 18 with a being equal to 1 over sigma. Therefore, it will be a moment generating function of random variable x evaluated at point 1 over sigma times t, but we still need to carry this factor, the exponent of negative mu over sigma times t. And at this stage, we are to use this formula for MGF of general normal variable. Let me rewrite this. Okay, so mx of t is the exponent of mu t plus sigma squared times t squared over 2. Therefore, a moment generating function of this standardized variable y of t should be, first of all, exponent of negative mu over sigma times t times moment generating function of random variable x evaluated at point t over sigma. So therefore, we need to use this formula, but with t replaced by t over sigma. Hence, what we are getting will be the exponent of mu times t over sigma plus sigma squared times t over sigma squared divided by 2. And we still need to carry this exponential factor, the exponent of negative mu over sigma times t. So, and we multiply these exponents, but we just need to add these guys. Yes, so what we realize is that this negative mu t over sigma and positive mu t over sigma, they cancel out. Sigma squared here in numerator and sigma squared here in denominator also cancel out. And what we obtain at the end is that it's simply the exponent of positive t squared over 2, which is MJF of standard normal random variable z. And due to the uniqueness theorem and the fact that we showed that moment generating function of such standardized variable y is the exponent of t squared over 2, which is the same as the moment generating function of standard normal variable z. Hence, the distribution of standardized variable y is standard normal, which easily follows from the uniqueness theorem. Let us talk more about the normal distribution. It's the most important class of probability distributions, as you might recall. So we have general normal variable, and then we add a constant, and we scale it also. So we consider a linear transformation of general normal random variable. And our goal is to find the distribution of such a linear transformation of general normal random variable. Of course, it's possible to differentiate the probability density function, but these analytical techniques of moment generating functions makes our life particularly simple. That's why it is important to develop these new methods, which might be difficult at first, but then you realize that it pays off to invest time in studying this analytical technique, because it just becomes applicable to so many situations. So what we obtain is that moment generating function of a plus bx of argument t is e to the power at times the moment generating function of normal variable x evaluated at point bt. Therefore, it's e to at times moment generating function of this guy, which is the exponent of mu times t, but instead of t, we need to use bt plus sigma squared multiplied by bt squared over 2. And let us simplify this expression. It is going to be the exponent of a plus b mu times t plus b sigma squared times t squared over 2. Let me square this formula. Okay? So, and then for general normal variable, moment generating function is expectation of constant times t plus certain positive constant multiplied by t squared over 2. And when we look at this guy, we identify it as MGF of normal random variable with mean A plus B mu and variance B squared times sigma squared. Therefore, what we obtain here is that random variable y, which is A plus bx, is normal with mean A plus b mu and variance b squared times sigma squared. Again, this follows from the uniqueness of characterization. There is a unique correspondence between distributions and their moment generating functions. We identified the moment generating function of a linear transformation of general normal random variable as the moment generating function of a different normal random variable with mean A plus B mu and variance B squared times sigma squared. So since MGFs are the same, then the distributions must be the same. That's the end. So the next result is of a particular importance for the theory and applications. Let me first talk about the theory. So here we deal with a linear combination of two normal random variables, and then we add up a constant c. But when we have normal variable and we add a constant, we just move the center along the horizontal axis by constant c. So it's not, c here is not really that difficult to handle. So we can for now assume that c is 0. Yeah, so it's really linear combination of x1 and x2. Even a and b are not that important because ax1 and bx2 are going to be also normally distributed. What matters here is the sum of two normal variables. And that's what I'm going to talk about now. What already follows from our previous discussion is that ax1 is normal with mean a times mu1, because x1 is normal with mean mu1 and variance sigma 1 squared. So when we multiply by constant, so our constant a is here is 0, so we multiply by constant. Therefore, what we do, we multiply the mean by constant and we multiply the variance by squared constant. So therefore, ax1 is normal with mean a mu1 and variance a squared times sigma 1 squared. And similarly, random variable b times x2 is going to be normal with mean b times mu2 and variance b squared times sigma 2 squared. So bx2 is therefore distributed according to normal law with mean b mu2 and variance b squared times sigma 2 squared. And x1 and x2 are independent, hence ax1 and bx2 are also independent. Therefore, by the multiplicativity property of the moment generating functions of the independent random variables, moment generating function of ax1 plus bx2 at the value of argument c is m of ax1 at point c times m of bx2 at point c. And random variables ax1 and bx2 we already identified. They're specific normal random variables. And then we have a constant c added. Okay? I will not deal with it right now. I'm going to comment on it later on. But what I'm going to use now is a specific form of moment generating functions of such new random variables ax1 and bx2. I still need to keep this formula, although I hope you might have already memorized it by now. So, therefore, moment generating function of ax1 plus bx2 of argument t is the exponent of the mean of first variable x1, which is a times mu1 times t, plus the variance a squared times sigma 1 squared times t squared divided by 2. This is the first MGF times the MGF of bx2, which is b times mu2 times t, plus b squared times sigma 2 squared times t squared over 2. So we use this formula with mu being equal to b mu2 and sigma squared being equal to b squared times sigma 2 squared. And what remains is to do cleaning. So you have two exponents. So and you have linear and quadratic terms. So therefore, it's going to be the exponent of a mu1 plus b mu2 times t plus a squared sigma 1 squared plus b squared times sigma 2 squared times t squared over 2. So when you look at this guy, you identify it as moment generating function of normal random variable with mean a mu1 plus b mu2 and variance written here, a squared sigma 1 squared plus b squared times sigma 2 squared. That's a beautiful property which I derived. So a linear combination of independent normal variables is also normally distributed. And then you can generalize this result to the case of an arbitrary fixed number of independent normal random variables and obtain that such a sum of independent normal variables is also normally distributed. And of course, mean and variance should match. If they're independent, then expectation, of course, equals the sum of expectations, and the variance of the sum of independent variables equals the sum of their variances. So this part is easy, and it's consistent here. But what matters is that this family, this normal family, is closed under addition. So conclusion. The normal family is closed under addition. And the converse of this result is also true. And it's known as Cramer theory. So Harald Cramer. So proved this result around, I think it's around 1936, like this special cases of the results on the arithmetic of probability distributions were all derived around 1930s. Yeah, but they were general results. Say, my general theorem on this stuff was proved in 2004 and published in Communications and Statistics Theory and Methods. So what basically Cramer proved is that if you want to decompose normal random variable into independent components, then these components are bound to be normally distributed. You can get nothing else but normality. And proving the converse is not that simple. It uses subtle properties of the normal distribution, which is such that it doesn't have decomposable components. Like for Poisson and normal distributions, if you split them into independent components, you are bound to preserve the structural property of a specific class. It's really a very beautiful result. So of course, in 1930s, like he didn't dream about it being so useful, but later it was already in 1970s. Robert Merton, the Fields Medalist in economics, who shared Nobel Prize in 1997. Yeah, so he proved what is known as Merton mutual fund theorem. So where you deal with linear combination of normal variables and you use various properties of choosing weights of your investments and the so-called Sharpe ratio, Sharpe portfolio performance measure. So the outgrowth of Merton mutual fund theorem actually really is this fundamental result of the arithmetic of the probability distribution. So those who specialize in economics and finance might want to read more about Merton mutual fund theorem or ask me the corresponding questions. And the simple part of this problem is adding up constant C. So it's really nothing here. So when you add C, so it will be C plus AX1 plus BX2 of argument T. So you simply get this factor e to Ct times m of AX1 at T times m of Bx2 of argument C. So therefore, what is being added is this extra factor e to Ct here. Or you can take it inside here. So you simply will get C plus mu1 plus bmu2 times T plus the same coefficient for the quadratic term. And this is MGF of normal with mean C plus mu1 plus bmu2, and the variance is squared times sigma 1 squared plus b squared times sigma 2 squared. So adding a constant is not really a big deal at all. Okay. And we now need to concentrate on pause, please. Okay. Okay. So I now want to discuss this important relationship between the standard normal variable and chi-squared variable with 1 degree of freedom. And this relationship is really clearly derived by using the techniques of moment generating functions. There are other methods, like we can solve this problem using the brutal force method, but it's actually much nicer to use the techniques of moment generating functions and then the uniqueness theorem. And the result is indeed beautiful. Specifically, I'm going to show that the square of standard normal variable z squared, which I denote by random variable y, is chi-squared random variable with 1 degree of freedom. But I also want to remind that for moment generating function of chi-squared variable with new degrees of freedom, the MGF is 1 minus 2t to the power negative nu over 2 for t less than 1/2. So I'll show that in our case, nu is simply equal to 1. Okay. So I consider, so I fix t and my random variable z squared is clearly positive, so I fix t, say, greater than 0. Well, it doesn't have to be the case, just fix t. We'll figure out the range later on. Yeah? And then consider non-random function g of u equal to e to t times u squared. Hence, g of capital Y, where Y is z squared, is e to t times z squared. So, and this is, of course, a new transformed random variable. And expectation of g of capital Y is, of course, the integral from negative to positive infinity of g of, so it's actually g of Y. But actually, it's nicer to write that it's g of z. And y is z squared, but really here it's little g of z. So I put this argument z squared. Yeah. So expectation of g of capital Z is the integral from negative to positive infinity of this function g of argument u times the PDF f sub capital Z of little u du. That's the shortcut. This is the shortcut formula for expectation of a function of a random variable. And then g of u is e to tu squared. And this guy is the bell-shaped curve. Okay. So what I obtain is that expectation of g of capital Z, which is expectation of e to t times z squared, which is nothing else but a moment generating function of z squared at point t, is my integral from negative to positive infinity of e to tu squared. That's what my g of u is. Times the PDF of standard normal, which is 1 over the root of 2 pi times the exponent of negative u squared over 2 du. And they can combine these two factors in one. So what I'm going to do is to take out 1 over the root of 2 pi, and then it will be integral from negative to positive infinity of the exponent of negative u squared times 1 minus 2t over 2 du. And what I'm going to do is to make change of variables. V equal to root of 1 minus 2t times u. And also for this integral to converge, 1 minus 2t should be positive. Otherwise, I'm in trouble. If it's negative, I get positive sign here, and this is going to be the exponential function that blows up at positive and negative infinity. So that's why I get such restriction on the domain of the argument t. So let's see what we are coming to. Okay, so I implement this change of variables, v equal to root of 1 minus 2t times u. Therefore, du is equal to 1 over the root of 1 minus 2t dv, and this guy can be factored outside, and therefore, moment generating function of z squared at point c is going to be this root, 1 over this root, taking outside, times the integral from negative to positive infinity, because v will also vary from negative to positive infinity. I can take this 1 over the root of 2 pi back inside the integral. This is going to be negative v squared over 2 dv. So it will be integral of 1 over the root of 2 pi times e to negative v squared over 2 dv. And this is the total probability for standard normal variable z. So therefore, this integral is equal to 1. Yeah? And therefore, the moment generating function of the square of standard normal is 1 minus 2t raised to the power negative 1/2. But I also have this limitation that 1 minus 2t is positive, which means that 1 is greater than 2t, or t is less than 1/2. So this is true for t less than 1/2. But what I get here is nothing else but MGF of chi-squared variable with 1 degree of freedom. But this is MGF of a chi-squared variable with 1 degree of freedom. And the conclusion I'm going to make is that z squared is distributed as chi-squared variable with 1 degree of freedom. And of course, chi-squared variable is a special case of gamma. And next, I consider a sequence of chi-squared variables y1, y2, yn are chi-squared distributed with degrees of freedom nu I respectively, and I varies from 1 to n. And my goal is to find the distribution of such a sum. Okay? To this end, I remind that for each component, MGF is 1 minus 2t raised to the power the number of degrees of freedom nu I over 2. And then I use the multiplicativity property. By multiplicativity property, the moment generating function of such a sum of chi-squared variables, which I denote by W at point T, is the product of moment generating functions of random variables m sub yi of t, which is the product over I from 1 to n of 1 minus 2t to the power negative nu I over 2. And clearly, so it's 1 minus 2t raised to the negative power, and we multiply this guy, So what actually it happens, it's going to be simply 1 minus 2t raised to the power negative 1/2 times nu1 plus nu2 plus etc. plus nu n. And for each of these guys, the argument c should be less than 1/2. Otherwise, things blow up. And then when we look at this expression, we identify it as moment generating function of chi-squared variable with nu1 plus nu2 plus etc. plus nu-n degrees of freedom. But this is MGF of chi-squared variable with nu1 plus nu2 plus etc. plus nu-n degrees of freedom. And the conclusion I'm going to make is that the sum of independent chi-squared variables is also chi-squared distributed. So k squared 1 with new 1 degrees of freedom plus k squared with new 2 degrees of freedom plus etc. plus k squared variable with index n with new n degrees of freedom is distributed as k squared variable with new 1 plus new 2 plus new n degrees of freedom. So these guys are all supposed to be independent. And what it means is the additivity property of the class of k squared random variables. So this is the additivity of the class of k squared random variables. So the converse of this assertion is also true, but under certain conditions, namely, there is an important Cochrane theorem which gave rise to the modern theory of experimental design that I want to comment on now. So the converse is William Cochrane theorem, proved or published in 1934, that if we want to decompose a k squared random variable with new degrees of freedom into independent and k squared distributed components, then the sum of the corresponding degrees of freedom of the individual components must match mu. So in other words, if we add up the sum of individual components of such elements of decomposition, nu1 plus nu2 plus etc. plus nu n, then such a sum must be equal to the number of degrees of freedom nu of such original chi-square distributed random variable. So this result is an apple from the same apple tree as Cramer and Rykov theorems on the decomposition of normal and Poisson random variables, but it's a kind of sorry, it's a kind of weaker result. Like I worked in this area of distribution theory around 2004. So I should also say that this result on the properties of the class of chi-squared random variables gave rise to the modern theory of experimental design. William Cochrane actually worked in an agricultural farm in UK on various agricultural experiments. And this research came up from his studies on the data for agricultural trials. And there are numerous other things that are related to this. For instance, corollaries from Cochrane theorem are that for a sample from a normal population, the sample mean X bar and the sample variance S squared are independent. Subsequent results would be Theo-student distribution, which I'm sure many of you are going to learn about in the follow-up course Status 60. The result actually employed is, again, independence of the sample mean and sample variance when we have a normal sample. These are all corollary of this remarkable William Cochrane's 1934 theorem on the decomposition of chi-squared random variables. And since I mentioned this result, I want to say just a few words about these quantities because it's relevant now. So x1, x2, xn is what's called SRS, or a simple random sample from normal mean n mu sigma squared population. So this means that x1, x2, xn are ID random variables which are normal with mean mu and variance sigma squared. So x bar, of course, x1 plus x2 plus xn over n. So this is what we call the sample mean. But it's really a random variable. And then we consider s squared, which is 1 over n minus 1, times the sum over I from 1 to n of xi minus x bar squared. So this is what we call the sample variance. And of course, if x1, x2, xn are numbers, so the sample variance is a number. But if there's just a random variable, so it's also a random variable. So we of course know that expectation of x bar is mu, expectation of s squared is sigma squared, but a corollary from Cochrane's theorem is that x bar and s squared are independent in the normal case. And also there is an important result that n minus 1 times the sample variance s squared over sigma squared is actually chi-squared distributed with n minus 1 degrees of freedom. So that's why chi-squared distribution is so important in statistical inference, because this is the distribution of the scaled sample variance. That's what we use to make inference about population variance. And this all originated from 1934 result by William Cochrane, so which I want to remind. So this is the converse of this straightforward result. And so this is the additivity property of the class of chi-squared variables. And in some sense, it's if and only if result. Okay? And I would like to remind that I also discussed the additivity of the class of gamma variables with the same value of intensity lambda. It's an apple from the same apple tree as this class of properties of chi-squared distributions. It's just a special case. And let's talk about this question. So we have independent, but not necessarily identically distributed random variables xi with mean mu I and standard deviation sigma I. Then we standardize these guys and consider xi minus mu I over sigma I, and then we square them. The question on the floor is the distribution of such a sum of squares of standardized general normal variables. It's not that hard if you're able to follow the main ideas of this and previous lectures. So what actually happens is that xi minus mu I over sigma I is standard normal zi. If we square these guys, we get square standard normal, which is chi-squared distributed with 1 degree of freedom. And therefore, the y, this sum y is the sum over I from 1 to n of zi squared. And if xi's are independent, then zi's are also independent. Therefore, this is going to be the sum of n independent chi-squared variables with 1 degree of freedom. And we have this additivity property of the class of chi-squared variables. Therefore, it's chi-squared distributed with n degrees of freedom. That's it. So we need to remember, of course, that standardized general normal is standard normal, and standard normal squared is chi-squared distributed with 1 degree of freedom. And now I want to discuss the other result of the arithmetic of probability distributions, which is clear actually. Intuitively, this is pretty clear. I have two random variables, x and y, which are independent and binomially distributed. So x is binomial with n1 trials and probability of success theta in a single trial. And y is also binomially distributed with the number of trials n2 and the probability of success in the single trial also being theta. So theta here and there are the same. And the question on the floor is to show that such a sum of two independent binomial variables with the same probability of success is also binomial with the same probability of success theta in a single trial and the number of trials being n1 plus n2. And this result makes intuitively perfect sense because we have two binomials. Probability of success is the same. So we just toss a coin. And one times the odds for a head are theta per single trial. And then after we finish with n1 trials, we start tossing the same coin again. You toss it independently and two more times. The probability of success is still theta. Nothing changes really. It's like tossing the same coin n1 plus n2 times with the same probability of success theta and looking for the total number of successes. But it's going to be again binomially distributed variable. So intuitively it's clear, but how to prove it? The right approach is to use the techniques of moment generating functions and also to employ this uniqueness of characterization theorem. What is the moment generating function of binomial variable? It's not that hard to figure out. So let me consider just a single trial. So it's B of 1P. It's a single trial. So M of B of 1P of argument T is what? It's expectation of e to t times b of 1p. And b of 1p is either 1 with probability p or 0 with probability 1 minus p. Hence, this expectation is e to, so it's going to be the sum of x from 0 to 1 of e to t times x times p of x, which is e to t times 0 multiplied by 1 minus p plus e to t times 1 multiplied by p. Hence, it's 1 minus p plus p times e to t. You can rewrite it as 1 plus p times e to t minus 1. This is for a single trial. But then BNP is nothing else but the sum of n independent Bernoulli trials. So BNP is B1 of 1P plus etc. plus Bn of 1P. So these are individual Bernoulli trials with the same probability of success P. So P is the same as theta. So it's a probability of success. Hence, moment generating function of BNP, of the binomial variable with n trials and probability of success in the single trial P, is 1 plus P times e to t minus 1 raised to the power n. And then we have random variable x, which is b in 1 theta. Random variable y is b in 2 theta. So theta is the same as p, so it's between 0 and 1. These guys are independent. And hence, moment generating function of the same x plus y of argument t is the product of moment generating functions of these variables. And it will be 1 plus p times, so p is theta, it's 1 plus theta times e to t minus 1 to the power n1 times 1 plus theta times e to t minus 1 to the power n2, and it's the same base raised to power n1 and n2 respectively, so therefore it can be rewritten as 1 plus theta times e to t minus 1 raised to the power n1 plus n2. But again, it's MGF of binomial experiment with the number of trials n1 plus n2, and the same probability of success theta in a single trial. And then we use this remarkable uniqueness theorem that states that if we identified moment generating function of our distribution, then it's the same as identifying the distribution. Hence, our distribution of the sum is binomial with n1 plus n2 trials, and the probability of success theta in a single trial, the result that makes a perfect intuitive sense. Just toss a coin n1 times and then toss it again n2 times. That's it.